Now the next SOP lecture, I am inviting to the Professor Gianna Paulo Semularum, Polytechnical Tornio. Gian Paulo Semularum is currently Associate Professor at the Polytechnical di Torino. He has been recently visiting professor at the University of California, Berkeley, 2014-2016. He obtained his MS 2005 and PhD in 2008 from the University at Buffalo, Sunny in United States of America. Graduate come in Civil Engineering, University of Rome, September 2001. He is the chair of the SHMMI Committee on the Resilient Structures and Infrastructure CORSI of the International Society for Structural Health Monitoring of Intelligent Infrastructures. He is also SHMIA Council member of the government body of the International Society for Structural Health Monitoring of Intelligent Infrastructures. He has been invited to 10 keynote lectures and 30+ seminars worldwide. He has authored 73 journal papers and 192 conference papers, 17 book chapters, and 5 books. Sir, research interests are community disaster resilience and sustainability to natural disasters. He has been awarded with a grant of 1.3 million euros by the European Research Council for the project Ideal Rescue ERC 2014 STG. He is editorial board member of the several ISA journals, Selector Awards, PIP Achievement Award for Young Engineers 2011, Seed Grant Award from the Stable Energy Institution of UC Berkeley 2015, Best Presentation Award in 2017 at SHMIA 8 Brisbane. So, with this, we are inviting to start to present his SOP lecture. Thank you, sir.
Okay, so first of all, I would like to thank you very much, all of you, for inviting me to this conference. I would have liked to come to India and for my second time and meet you all in person, but unfortunately, due to this pandemic situation worldwide, we cannot. However, I'm really enjoying the organization of this conference. I really like the format and the way it has been set up. So. Congratulations to you for this. And so I also apologize because this presentation was supposed to be yesterday, but I messed up with the time zone in India and Italy, and so I asked to postpone to today. So that's where I am now. Okay, so good morning still, everybody. One moment. Okay, so as you mentioned in my CV, part of the research I'm going to show you today is part of a European project which started in 2015 and is a IRC grant. And through this grant, we were able to collaborate and start a deep collaboration also with the University of California, Berkeley, and in particular with one professor I would like to acknowledge because he passed away a few years ago, which was Professor Steve Main, and with the SIM Center, as well as with the Pacific Equation Engineering Research. So part of the research you will see, it's also work that I've done with my students while they were there in Berkeley. As I mentioned to you, this grant allowed me to develop at the Politecnico di Torino in our university a virtual reality lab in which basically we were able to use a 3D printer as well as a movable shaking table that can be used to do some tests that you will see in this presentation, and also a supercomputer to do large-scale simulation. Now, the presentation outline is introducing the concept of resilience, and in particular, one of the framework that we deeply develop in collaboration with MCR, which is the people frameworks. And then I will show you some application to large-scale cities and how this can be also applied to developing countries, which is part of my current research nowadays. So resilience. Before we start, I just want to to show you this graph to show the tendency of the last 100 years, how the natural disaster increase worldwide in different continents, but there is always the same trend. And when we compare natural disaster towards man-made disasters, the ratio is 2 to 1. For example, this slide is not updated, but in 2016 we had about 600 600 natural disaster and 300 man-made. And this is the distribution of natural disaster divided by continent. As you can see here, the main component, the earthquake component, is in Asia. We are in Europe, and in Europe, actually, the main natural hazard are storms, as you can see, and flood. However, that small green line that you can see in the Europe belongs to mainly 3 countries, which is Italy, one of those. The second is Greece, and then Turkey. And I'm, as a matter of fact, I'm studying earthquakes. So part of the example and case studies that you will see are related to earthquakes. Now, this concept of resiliency, it's an old concept if we go back in the literature, and it comes not from our field, but from a psychology field, actually. Then it has been applied in engineering as the property of a material to bounce back. But recently, in the last few decades, I would say, the concept of resilience has been extended in civil engineering. The line here is showing me that I have only 5 minutes left. Is that right? Or, okay.
No. You have 25 minutes more.
Okay. All right. So resilience, it's a well-known concept that has been spread worldwide. There are different programs in US, in Japan, New York. We have the 100 resilient cities with the Rockefeller centers and so on. But when we go back to the initial definition of resilience provided by Hemsier, is the area underneath this functionality curve, which we want to maximize. This concept is well known, so I will go kind of fast. And through this year, since 2003, that the famous paper of Bruno et al., this curve has been stretched up and down by different researchers, including plateau, step functions, if you're looking at residential buildings, and also including the aging effects, for example, or the coupling effect of different lengths in the same earthquake. Now, the main issue is how to measure resilience. So we have different type of indicators which can be classified according to the hazard, to the temporal, to the spatial scale. I will not go into the details, just to show you that there are many indicators, and there are also many approaches. Here probably is not completed this list, but I grouped mainly them in 2 main groups: the bottom-up approaches and the top-down approaches. Here in the bottom-up approaches, you can see a series of methodologies like the CART or the TRIV, and they are both can be either qualitative, quantitative, including all hazard or only few specific hazards and so on. And then we have top-down approaches. Even here we have the ICO framework for actions, the SPOR, which is the San Francisco Planning for Urban Research Association, the BRIC, which is another indicator from Susan Cutter, and at the end we have our model, which is the People Resilience Framework. And if we focus on the People Resilience Framework, basically this is a GIS approach which consider each infrastructures or dimension as a layer. And these layers are 7 in the People frameworks, and that can be combined. There are 2 ways to combine this information. One is a scenario-based approach, in which basically you are supposed to have an hybrid model of your community, where you have physical lifelines and non-physical lifelines. So you can model both infrastructure like water distribution, power distribution network, but also emergency authorities like search and rescue, first aid authorities, policemen, and so on. And once you have this huge model and you calibrate the model, you can then measure certain performance using the People frameworks and compare this with certain performance level. If you're not satisfied with that, you can act on the 4R, which are robustness, rapidity, resourcefulness, and redundancy, in order to improve this resilience of the entire community, and then use this for designing. Of course, this process is quite complicated because it requires the model of your community. If you don't have that and you want to use in a simpler way the people framework, you can use an indicator-based approach in which basically these indicators for each one of the dimension components and subcomponents you can see here, you have a corresponding indicator because we identified something like more than 125 indicators, and we didn't want to reinvent the wheel, so we combined them using data from census. And by doing that, we show here a simple application to our country, in this case Italy, and we were selecting some of the indicators which belongs to the people framework, which we can find in our ISTAT. And by doing that, we will plot the chloroplat maps, sorry, of Italy. And as you can see here, there are a series of indicators, and by doing that, we could get the resilience of the emergency response of the reconstruction phase. As you can see here, some regions are more resilient to emergency response, in particular the central part of Italy, because they have more experience with respect to the northern part, which is the richest part, and so they have performed better in terms of reconstruction phase, for example. Now, all this information has been combined in a software, which, because we are at the end of the project, we are going to release it, so it will be public available. And in this software, we uploaded one community. The community that you're seeing here is the city of Turin. At least it's a resemble of the city of Turin, in which we implemented certain type of data that were available. And whenever these data were not available, we make up this data, in particular for the power and the gas network, which are sensitive information and we couldn't share. We have to make a reasonable network, which is probably compatible with the existing one. I will go quickly, and then with this model, for the first thing we did a large-scale simulation of what we call ideal city. This is a city of about 900,000 inhabitants, and with model all the critical infrastructure from the hydraulic network to the building. I will go quickly about description of how we collect the data from the buildings. Basically, we collect information about the year of construction, geometrical data, and some additional information about the economy. All this information were taken from some website, from the City Hall, as well as from some European project. And about also the topology approach. Most of the buildings in Turin are made of masonry. And as you can see here, we categorize them according to the technology, to the topology of buildings. Then we look also at the seismic zone. Through the years, the earthquake zone changed, and we look also at the resistance of the masonry panel according to the opening. So we define a sort of backbone curve, a capacity model, which we identify two capacity models, one for reinforced concrete and one for masonry. And we, through some energy approach, we were able to identify these 4 points of the curve. I will not go too much into the details. I will skip some of those slides about the methodology, but at the bottom you can see here there is a paper that now has been published, so you can have it if you are interested in the details. So by doing that, we apply the same concept also for the masonry by converting the panel of masonry in an equivalent concrete frame, and we were able to then model the multi-story building with an equivalent single degree of freedom nonlinear system. And this is the Takeda model that we use to model each single buildings. And we implement all this in OpenSys version in Python, and we run some analysis. Here are some examples by using the supercomputer that we had in our research group. So we look at the speed, and we try to use ways to implement or to make the simulation faster. In particular, we try to use the GPU instead of the CPU, but there were some issues with OpenSys, and at the end, we decided not to use GPU, but to keep going using CPU. The main idea here is that we had something like 80 cores, to each core one single building, which was one single degree of freedom system, and then run the simulation, and then we assign, once the simulation is done, the new building to that. By doing that, we compare the results between GPU, CPU, and the multiprocessing techniques, and we figured it out that at the end the CPU for us was faster than the CPU single core, but also of the GPU. Here are some specific calculation looking at the ratio, and we figured it out that as the speed of simulation set up around the speed of 37, the number of buildings processed remains the same. These are some analysis, output of our analysis. It's an example of an earthquake. I think this one was at Centro, and we look only at one part of the city. And what we are plotting here is the top interstory drift, which is directly correlated to damage. So what we did, we did some tests assuming an epicenter in the southeast part of the city. And then we simulate 4 earthquakes, Centro, Pinoy, Kobe, North, 2 far field and 2 near field earthquakes. And we compare these results with the building archetypes and the year of construction. As you can see, in red is the downtown area, which is mainly ancient old masonry building. And when we ran our simulation, we figured out that the most vulnerable part was downtown, as expected. And far from the epicenter, we are low damage. And also the newest part of the city, which is in the south part, even if it was close to the epicenter, experienced low damage. So everything at the end was what as expected. Here are some results comparing the year of construction with damage data and so on. Now, the main issue, however, when we calculate downtime, when we calculate resilience, is how to estimate downtime. Now, we apply this concept of downtime to residential buildings in developing countries. But today, in this presentation, I will show you how we apply the same concept in developing countries. Because, as we know, most of the vulnerable countries are the ones that are developing, and because usually are mainly affected from natural and man-made hazards and poor quality of construction, and the fact that sometimes we don't apply any seismic design cause a lot of that. These type of buildings are here. I simply categorize them in dog buildings, which are basically low energy buildings, which are fireproof and biodegradable. And they are perform actually pretty well against earthquake. Then we have the stone masonry buildings, which is a common type of building in rural areas. However, you need to provide certain retrofit techniques in order to perform well after doing earthquakes. And then we have bamboo buildings, which is green, biodegradable, and eco-friendly material, and is usually a good alternative for steel when steel is not available. And there are also prefabricated bamboo buildings and concrete surface ram and earth core buildings. Now, how do we estimate downtime for this type of buildings? So the main challenge is due to the fact that we have to deal with imprecision and uncertainties. Uncertainty that comes from the high numbers of involved parameters, by the accuracy of the available data that sometimes is not sufficient, and by the fact also that there are no models developed for this type of buildings in developing countries, and most of the time this downtime is affected by subjectivity and based on experience. So what we try to apply is a fuzzy logic approach to estimate the downtime for these buildings in developing country. The fuzzy logic, I will not spend too much time. I assume the fuzzy logic approach has been granted, but however, this methodology was developed by Zadeh in 1965 and is used to give or to quantify certain, sorry, one moment. Is used to quantify certain degree of uncertainties or certain measures that are qualitative only. And this is the scheme that we use. And basically, the methodology that we apply is based on estimating first the post-earthquake building evaluation using a rapid visual damage assessment. And then we build a building damageability model, which is based on a hierarchical rule and through which we use inference to combine the indicators that come from the fuzzy logic. And then we finally estimate downtime, combining three values of downtime: the downtime due to repairs, downtime due to delays, and downtime due to utilities disruption, which is the classification given by one professor in UC Berkeley. So in the post-earthquake building evaluation, basically this RVDR aims to analyze the damaged building and gather information of the building, design characteristics and components, and is used to also to describe the buildings. Then what happens is we have the building damageability model. Basically here in these figures, in this slide, it shows a scheme that show the two main components to the two main modules, which is the highlighted in gray, which is the site seismic hazard and the building vulnerability. The site seismic hazard basically get information mainly from the background of acceleration, and while the building vulnerability takes into account two aspects. One is the post-earthquake condition, and the other is the structural system. The structural system, it considers the type of floor, the type of roof, the type of construction, while the post-earthquake condition is related to the building condition right after an earthquake. If it's partially collapsed or completely collapsed, if the story are out of plumb or damage to specific structural members, and so on. And this information are combined to get the building damageability. And then through these three columns, what you see up here, you will get basically the downtime due to repair, due to delays, and due to utility disruption. Now, to get this information about the downtime, we try to get the information of downtime taken from PACT, which is a software provided by the FEMA. It's a US Federal Emergency Management Agency. But this data were not good for developing countries. So we collect data from basically survey that we perform in some of the earthquake which happens in Nepal in 2015. And we combine them to get the downtime due to repairs. This is the repairs, and for each components, we can calculate for structural and structural components using the methodology, which is the same already, to calculate this downtime. And finally, we get this probability of non-exceedance and the downtime due to delays. And finally, we have also the downtime due to utility disruptions that can cause by being inoperative some of these power network or transportation network to delay all the process of the restoration. Somehow, to take into account the utility disruption, we use some fragility curves, which has been built based on earthquakes from collected from 1960 until nowadays, and our simplified approach, but it's the best that we could do with a simplified model. And then once we evaluate these three downtimes, we combine them to get the final downtime for developing countries. As I say, I applied this concept to the data we had in Nepal, and these are some characteristics of the earthquakes. You see, there were more than 500,000 buildings damaged and collapsed, and 9,000 people died. So we we focus only on residential buildings in this specific case, and here is the distribution of the type of residential buildings that were damaged and that were without missing information. So at the end, the number of buildings analyzed were 9,000, and as you see, of these 9,000, 38 were reinforced concrete, some were brick and mud, 37, and only a small percent were adobe, 2%, and so on. So with this database, basically, we look at the behaviors and the typical common failure for certain type of buildings. In particular, we focus on reinforced concrete buildings, so only one specific type. And the masonry building has some issue which are common also in Italy, which is the out-of-plane behavior, and also the fact of missing black box scattered box behaviors in the upper floor. And this is the results of our analysis, the building damageability calculations. As you can see here, while increasing the PGR, the number of damaged buildings increase, in particular in the medium damage level, and as you can see here. And here are some results related instead of the downtime estimations using the methodology I just described, which is based on fuzzy logic. As you can see here, for an earthquake with a PGI of 0.73 G, the time needed to recover is more than, as you can see here, 4 years, and which is pretty much what is happening also nowadays. Okay, and then we have a series of measures to improve resilience in developing countries. So we can work on policy and regulation, some techniques like base isolation, low-cost bubble frame, confined masonry, low-cost housing system, and so on. Policy and regulation means also in implementing simple construction practice to reduce the risk of collapse, educate private owners, adopt approaches based on disaster risk regulations. For the base isolation, well, in developing countries, we can use recycled rubber fiber reinforced bearings, which can have a rectangular shape because that's more easier to be manufactured. Or we can use simply sand rubber foundation layer on which the structure should be designed to withstand the earthquake acceleration, for example. Low-cost bamboo frame are also applicable in specific cases. And then we have confined masonry walls. In this case, we can use steel and cement in India, for example, or we can use reinforced concrete element like tie columns and tie beams. And then we have also sort of low-cost seismic intervention, like arch foundation used in walls that are supported on brick or stone masonry, or filler slab roofing system when the after part of the slab is subjected to compressive forces, and so on. Well, so this is the part related to the developing countries. Now I want to conclude just showing some parts coming back in our project about what we did on the transportation network. We analyzed basically for the city of Turin, which we call Ideal City, also the transportation network. We developed an efficiency matrix with more than 15,000 nodes, and we used two indicators: the average vertex degree as well as the efficiency, which is the shortest path between one node I and j, while we compare these results with 4 earthquakes, as you can see here: Northridge, El Centro, Cove, Aquinoa. Then we look at the interdependency. This is a picture we took in 2009 after L'Aquila earthquake, and you see the presence of debris due to the partial collapse of building make some of the roads unavailable. And these roads needs to be clean and available after an earthquake to allow the emergency rescue operation to act. So to do that, we decide to implement in a software which use the applied element method, the extension of debris caused by the collapse of some of these buildings. This is one building that collapsed in Amatrice during 2016 earthquake. So we modeled this in this software, and we were able to calculate using a geometrical formula the footprint area of debris caused by the complete collapse. And by using this with the debris area as you can see here in purple, we look if they intersect with the road or not, so that we can know in advance what are the roads that might or might not be available. Of course, this applies well only if they are full collapse. What happens is there is partial collapse. For partial collapse, we decide to use artificial intelligence. So using genetic algorithm, we were able in image detection to detect the extension of debris caused by the analysis of some specific pictures, as you can see here. And using this data and information, we were able to select some good picture with respect to the one that were not good by looking at 14 different earthquakes. And we compare these results by running our analysis, and we can see here what are the roads which were not available using this other approach. As you can see, Northridge, which is the near field, is the one where more damage. And then another aspect which is quite interesting and breakthrough in this project was the human behavior modeling during the emergency. Basically, no one so far ever modeled the panic effects and how this will affect on the emergency response. So we look at, by looking at some matrices, the memory, and take into account how the human behavior copes with dynamic changing environment. So basically, I will not go into the detail. For the paper you can see down there is the paper we wrote with Professor Main. We can look at the emotion, the memory, and belief, which are matrices which can be combined and calibrated using some surveys that we perform at UC Berkeley as well as at the Polytechnico di Torino with students. And then we were able to calibrate this panic model. Here is some application of mall which were located in Auckland, and the evacuation, and as you can see, these points are the agents which are moving out of the mall right after an earthquake through the emergency exit. And what we did, we learned our analysis with and without the human behavior model. And these are the results of the two curves. As you can see, if we don't consider the human behavior model, basically we end up underestimating the time of evacuation. We applied this concept not only to earthquakes, but also to blasts. There is another publication done in 2019, and we assuming that there were 2 blasts in the museum. And we look again at the emergency evacuation with and without the human behavior model. And this time the calibration was done with another type of surveys, but it worked well. However, we realized soon that these questionnaires were not good enough. We needed more unbiased evaluation, because everybody is it's a hero when he needs just to check a box, but in reality, maybe we will behave differently. So we decided to use some sensor to measure how is real reaction towards these dramatic or natural hazard events. But because we cannot experience an earthquake and collect this information, the only way is to use virtual reality. So what we did through a virtual reality mask vision of one of the scenarios that we were running to these people that were on a shaking table and were experiencing some of these shaking. And we were collecting biometrical parameters like the heartbeat, the respiration rate, and we were trying to collect data that we could be directly related to the panic. We made this during the research night in 2017 at the Polytechnico di Torino. We are going to repeat this experience now in September. After 4 years, finally the research night came back to the Polytechnico. This time we will do it at the Valentino Castle of the Polytechnico di Torino in September. And we will have more chance to get more data as well. So with this information, then we built an entire model, agent-based model of the city of Turin. And here are some initial preliminary visualization of these agents, which were running towards some shelters inside the building, but they found a roadblock, and so they decided to change the roads. Now, here is another view. And the interesting part of this, okay, you can see there are different colors. It depends on the state of injury of each single person. And what we see are the buildings which are different color according to the level of damage. Now, the interesting thing of this simulation is that through a virtual machine, we are also allowed to interact, so to be inside the simulation and interact with the simulation as well. So another project which we were involved, which was a side project with respect to the IDEAL rescue, is the IDEAL sensor project. In this project, we were analyzing the evacuation due to fire in a school building, which is located in Melzo, near the Milan. And here we built a BIM model of in Unity of the entire school. This is some view of this simulation model. We collaborate with the computer science research group of our university, and we did some analysis simulating the smoke propagation using FDS. Here are some simple examples of how to propagate and how we could transfer the information from FDS directly into Unity to run our simulations. And here is the steps that we follow to move from one software to another one. And finally, just to show you the final results, it's the smoke propagation that we can see inside the Unity model. So with this, we built virtual reality training platform for rescuers. Here it's our platform in our department, and here is the school. Basically, the test was in entering inside the school, which is fire, looking at the the map of the school and then get through the stairs and reach the person which were injured and then bring them back to the rescue point. So what we were doing, we were measuring basically the time needed to perform all these simulations. And we're going to repeat this experience also in September during the research with the same application. As you can see, this is exactly, I've been in that school, so it's exactly the same. They made a good job in actually representing the school the way it was. And basically they enter in the room with fires and they find the person injured on the left, and then they try to collect them and bring them out. Okay, I think I have not enough time to show you everything, so let me move a little bit faster to the monitoring part. Now, when we're talking about monitoring, because it's one of the research of our group, we look at two types of monitoring. Monitoring smart cities, which is something that you've seen, monitoring infrastructure, and monitoring people. So if we look at smart cities, we can use Internet of Things, as you've seen some examples here. When we look at the infrastructures, nowadays this is a very sensitive topic in Italy, because as you know, a few years ago, one famous bridges by Professor Morandi collapsed, and we were able to rebuild quite quickly, I would say, for Italy. And however, we studied this collapse using the software I mentioned you before, because we are collaborating with I.I.Sc, and we published this paper in Engineering Structures. And so here, basically, this collapse is now very clear that was due to the lack of maintenance. And so nowadays there is a big research project on monitoring bridges and tunnels to see how they perform and how they are aging through times. And here are some curves that proves how the investment costs in maintenance after the bridge became private in 1992 dropped significantly, and basically it was indirectly the cause of collapse. Now, this is for infrastructures. Let's go instead how you monitoring people. Now, we have a project which is called Ideal Sensor, and now it's called Ideal Drone. It's the second follow-up project in which basically we're trying to monitor the position of people inside buildings which are in emergency or need search and rescue operation. So in order to optimize the search and rescue operation of firefighters, which usually are involved in death during their operation because they are not aware of the building where they are entering and the risk that they are facing. So with this system, our idea is to let them know the position of the people who are in danger, their health condition, by knowing or transferring to the outside of the building the body parameters like temperature, heartbeat, and so on. The combination of this information will allow us to know if the person is injured, dead, or is in healthy condition. And so basically you imagine that if you are a firefighter, you're outside the building, you have a map of your floor in which in green are the people in normal condition, the yellow the people which are injured, and red are the dead people. So basically first responder, which are in blue, can then optimize the search and rescue operation and moves towards the people who are injured or are in health condition, so they can move them out and skip for now the people that are dead. So we implemented a series of anchors and tags to develop this technology. And here are some prototypes of this system. We made a test at the Polytechnic di Torino and patented the system. This is the final watch we use it. And this is the software to transfer the information from outside the building towards the outside. And this project has been also, we applied for extra funding by including also new technology, exoskeleton and augmented reality. Unfortunately, it wasn't funded last years, and there was also this issue of the COVID-19. So we are planning to reapply now with the new program, Horizon 2020. And in this project, we are involved also with some research group from South Korea, from I.I.Sc, in particular for the use of the exoskeleton. And with this, thank you very much for your attention. I will be happy to answer any questions. And most of the things you've seen are in these papers and in this book related to resilience. Thank you.
Thank you, Professor.
Hi, can you hear me? Yes.
Yeah, it was a very nice presentation, and I can say in just 30 minutes, we all can imagine, means from start starting the how disastrous the earthquake can be and how it can be managed, means the earthquake incidences in a very systematic manner. This first time we are all the things, all the parts we are seeing in one platform in just 30 minutes. So it is very good session, I can say, and it is we improved our knowledge and understanding about earthquake management and mitigating the not only the risk and but also the minimizing the damages also. I think Professor Ramana will tell further. Means
I think there is one question.
Yes.
And I
Yes,
think
sir,
that is some other person. It is not for him. Not for him. Okay.
no, in your simulation, did you model building because and Palazzo del Lavoro designed by Nervi? There is a question. In your simulation, did you model the buildings Torino Esposito and Palazzo del Lavoro designed by Nervi?
Okay, one moment. Yes, maybe I can hear you well better with this. Can you hear me?
Yeah, we can hear you.
Okay. Yes, we model the buildings, of course, because we are. I didn't mention we are talking something like 26,000 buildings, so we cannot go too much in detail. Okay, otherwise we will be running simulation for days, and this is not the purpose of this simulation. The idea is to develop a software or a tools that can be used to assist during the emergency the people, so that they have an idea which are the roads which are available, which are not available. So the information should be given quickly, in few hours, not in days. Okay, so the simulation needs to be fast. So first of all, of course, supercomputer help you, but also there is a limit from supercomputer. So you need definitely use a simplified model. So we used to say, I used to teach, in seismic engineering, that sometimes you don't need a Ferrari if you just need to reach, the bar which is downstairs, and so you can use your 500 Fiat. Okay, so in that sense, sometimes simplified model works well for what you need to do, and so we model each building with a nonlinear but single degree of freedom system, and we obtain this model from a multi-degree of freedom systems. So we made an equivalent transformation. It's something similar to the, I'm sure you're familiar with the pushover method of Professor Fiver, the N2 method, or CSM. So we try to simplify to run large-scale analysis. However, okay, one of my colleagues that is closer to my research and did something similar is Professor Shinsen Lu from Tsinghua University. He is doing the same model for Beijing, but he's applying a multi-degree of freedom system when he looks at the tall buildings, because there are many tall buildings in Beijing. So he's using a slightly different approach, but this is not our case, because most of the buildings in Turin are 4 to 5 stories, so it's pretty flat. So, but yeah, I mean, this is our approach. There are many ways, many groups that are working on large-scale simulation that use different ways to get to the same point. I don't know if I answer your question.
Ramana?
Sir. Okay, sir, actually, thank you very much. And especially this session is very good. And total two SOPs. One is, I think, the eminent professor Dipankar Chaudhary sir has given an excellent lecture. Especially, we learned many things, not only for me, and all maybe participants also. They may gain a lot of knowledge in the area of especially the peak particle velocity and how the uncontrolled ground-borne vibrations for the design of substructure systems. So theory, practice, and moreover, actually, Sarah has explained especially how the IS codes and the other Euro codes actually has to be implemented while doing the numerical modeling and at the time of characterization. Especially, Sarah has given excellent case studies of 2 cases. for especially heritage structures as well as metro train track, and I think it is very useful for this particular information for all the participants as well as the practice engineers. And another SOP lecture by Professor Gian Polo Samloro sir. This is a civil engineering approach to elevate and manage resilience against natural disasters in developing countries. I think we have to learn many things from this. I think first time I've seen one of the uh, earthquake. I think we can predict that one and assess those things in a numerical modeling and reality also. And it is very useful for all the earthquake and the dynamic soil dynamics profession. So in addition to that, there is a three presentations they have presented. The number one is numerical studies of dynamic loading on ballast railway track by the one is Panjal Mandani and from the Indian Institute of Technology. And this is especially at present days, I think Indian Railways, they are actually looking for the new technology for the construction of railway tracks. So without ballast, it is very useful that one. And I think that topic is good for in respect of dissemination of knowledge to the entire research fraternity. And another one is actually that is analysis of urban planning under different loading conditions. That is especially for soft and weathered rock. I think the rock itself lot of uncertainty. So I think with consideration of that uncertainty, if they will go forward direction, I think this is very useful, especially for the tunneling of nowadays. Actually, there is a need of tunneling system. So and they have presented. That is also one of the useful lecture presentation. And the last presentation, one more actually was given a case study by J. Prakaswal sir. That is regarding the application of wave propagation with the low strain oil integrity test. So this is also very useful and good presentation. So and moreover, I thanks to the especially organizing committee for giving this opportunity, and also I thanks to my extend my thanks to the Dr. R.P. Singh sir. In the morning onwards, actually he has guided properly. You have to come at the right time, and also I extend my thanks to especially Ravijakka sir and Alleviate sir also. I think 2 days before also he has given certain guidelines what we have to do in the session. Thank you very much for all the participants as well as for the SOP professors also. Thank you very much, sir.
Thank you. So we are at the end of the session. On behalf of the organizing committee, I thank all the speakers and the chair and co-chair for effectively conducting the session. We are very much thankful to Professor Cimarello, though he could not make it for making it today. And we learned a lot about his simulations. Very good, very interesting thing we could learn. Thank you very much. Thank you all. So now we'll adjourn and rejoin for the session, plenary session at 2 o'clock. Thank you. Thank you all. Thank you very much.
Thank you.